So we've had some great talks in this NOTSCON about community involvement and ethics in programming. And I have to say that it's possible that the only important thing that software people can do for society is to make bright, shiny things fly around the screen. And this is what this talk is basically about. It's about how do we make bright, shiny things fly around the screen. But there are no bright, shiny things flying around the screen. There's just a bunch of maths. And the interesting thing about this is that I am not a mathematician. I was one of the arty kids at school. I have A-levels in English, art, and French, I think. So that's both an advantage and a disadvantage. So I don't, all the maths I've got in my head, I've sort of painstakingly put in there. And the advantage of that is I understand that sometimes things take a slow, careful explanation. So if you require slow, careful explanation to understand all this stuff, then I may be able to help. If you're all maths geniuses, then you can just watch me flounder for the next 40 minutes, which is absolutely fine. The ancient Greeks were totally in love with circles. Circle was an image of perfection. So let's start with a circle. And one interesting thing about a circle is that a quarter of it is a right angle, and those are very useful for building bookcases and so on. And as we all know, a right angle is 90 degrees. And you might think, why such a strange number? I don't know if you ever wondered that. It's actually to do with the ancient Babylonians. The ancient Babylonians were in love with the numbers 6 and 60. And that was not arbitrary. The interesting thing about 60 is that it can be divided by a lot of numbers, 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30, I think. And that means that you get to do a lot of very interesting mental arithmetic tricks with it, which is up until about 1980 was very, very important for the human race. It's being able to do mental arithmetic very quickly and readily. And of course, we've all forgotten since, so it's no longer important. But it used to be interesting. And the same reason why pounds, shillings, and pence are actually a much better system than dividing a currency unit into 100, because you've got 240 subunits in a pound in the pound, shillings, and pence system. And that means that, for instance, you can have an exact third of a pound in pounds, shillings, and pence, 6 shillings and 8 pence. But I digress. If you ask a mathematician what's in a circle or how do you measure angles, they'll say, well, you did radians. And you go, oh, okay, what's a radian then? Is a question I often used to ask to mathematicians, somewhat bemusedly. And they say, well, there's 2 pi radians in a circle, which is 6.28 mumble, mumble, mumble. And it kind of looks like this. And you think, well, why would you bother dividing up a circle into 6.28 something, something, something? That's no way to build a bookcase, is it? That's not going to help you at all. And so just understanding what a radian is kind of like what I think is the first stumbling block of doing any of this. So I thought I'd just explain it really quickly in case the principal has passed you by. So suppose I'm called Mr. Green, which in fact I am, and I have 2 minions, Mr. Red and Mr. Blue, and I'm standing at the center of a circle, say a furlong in radius. And I send Mr. Blue out to the edge of the circle, and then I say to Mr. Red, I'd like you to follow Mr. Blue out to the edge of the circle, and then walk exactly 1 furlong round the edge of the circle. So you go 1 to the edge, 1 round the 1 to the perimeter, and 1 round the circle, and that gives you exactly a radian, which seems like a not stupid thing. It seems to have a kind of completeness to it, which is nice. Where are we going to next? Ah, yes. Okay. So when you're doing 3D maths, the most important thing to get your head around are these things called transforms, which are ultimately matrices, and we'll get onto those. In order to understand how rotation matrices work, you have to start with 2 really, really simple cases. So I've got a point at the eastern edge of my circle, and I want to rotate it round an angle to get to another point, right? So it's the simplest possible building block. And if you look at that, you've gone round the circle, but you've also, whilst you've done it, you've formed a right angled triangle. And even if you don't remember that much maths from high school, you will remember just a little bit of trigonometry probably that tells you that going this bit here, going along the x is actually the cosine of the angle you started with, because it's the ratio of the adjacent over the hypotenuse. The hypotenuse is 1, right? So it's actually the one that you went out to the edge of the circle with. And then the adjacent in this triangle is the x value of your rotated point. So x is cosine theta, which is easy, and y, as it happens, is the other one. It's sine theta, which is marvelous. So there you go. So this is a 30-degree angle, which happens to be pi over 6, because this pi goes halfway around the circle. So if you divide it in 3, then pi over 6 is 30 degrees. And those are values that you come up with. X is now about 0.866, and y is exactly 0.5 for reasons of deep mathematics, which I don't begin to understand. And you also have to do the other simplest rotation, and the other simplest rotation is if you start 1 to the north, which is a unit in the y direction. So if you start 1 to the north and you rotate through the same angle, then of course now x has gone to the left by minus sine of theta, and y goes up by the cosine of theta. And it's just simple properties of the triangles that you've got in front of you. And so it kind of looks like that. And this is great because we've now got 2 building blocks. We know that when you rotate around x, when you rotate a thing that goes off to the right, that's just like a unit vector in x, then we get a little bit of the new x from that rotation and a little bit of the new y from that rotation. And also, when you start off with the y being 1, being a unit vector going north, then you get a little bit of the x from the y rotation, a little bit of the y from the y rotation. And if you put them together, before we do that, interesting thing about vectors. So points in Cartesian space, you usually say something like 7, 8 is a point in Cartesian space, is a concept I think we're all familiar with. You can also think of them as vectors. So the point at 7, 8 is if you start at the origin and you go 7 and 8, 7 across and 8 up. So suppose we've got 2 vectors and they look like this in space. We've got 7, 8, and then minus 7, is that you can actually add them together. And when you add them together, you just sort of like unit add the two bits together. So the resultant vector, the c that you get by adding the first 2 vectors together, you just add the 2 components, the x and y, in place, and they're addable, which is lovely. Because if we want to rotate a point, say 7, 8, so we've already rotated points which are just on the x-axis or just on the y-axis. But if we want to rotate a point that is somewhere in 2D space, and we will get on to 3D, honestly, but if you want to rotate a point that's somewhere in that space, just decompose it. So you've got 7 going across and you've got 8 going up. So you've now got 2 of those vectors, and you can see they kind of look like that, and I've tried to, yeah. Vectors don't really belong anywhere in particular, so you can move them from one place to another. They're just an amount, a distance in an angle, but they don't begin or end anywhere. So you can think of them as being either there where it forms a triangle, or you can move them back to the origin. Interesting. Now, suppose we've got that original point, which is at 7, 8, and we want to rotate it around 75 degrees. 75 degrees, again, you can get by dividing, because it's a multiple of 15 degrees, and 15 degrees is pi over 12, because it's a 24th of a circle. And so 75 degrees is 5 pi over 12. So that's, I seem to have made 2 copies of the same slide. That's good. So the way you can do this is if you start off with the x component and rotate that, and then rotate the y component. So if we start off with the x component, then we know that the original x, which happens to be 7, plug in the values that we had before. The new x that you get from there is the cosine theta, and the new y that you get from there is the sine theta, multiplied by the 7, which is the value of that particular thing, of that particular part. And then you can do the same with the vertical component. So the vertical component contributes a bit to the x and y. In this case, it's minus sine theta and y cosine theta, and you get used to reciting those values. So you then have these two, so the pale blue and the pale green. I hope everybody's can see that in colour vision. I used to get in terrible trouble when previous colleague was here from from not labelling things when they're in colour. But you can see that we're trying to move the purple vector around, and we don't know exactly where it's going to land, but we do have two precise values for the x component being rotated and the y component being rotated, which is nice. And then you can just add them together. So you can add them together so it looks like that, or you can add them together and it looks like that. But either way, you end up with these two magical equations. The new x is composed of the bit that you get from rotating the horizontal component, which is x cosine theta, and the bit that you get from rotating the vertical component, which is minus y sine theta. And the new y, similarly, gets a bit from rotating the x component, which is sine theta, and a bit that you get from rotating the y component, which is cosine theta. So you've got these two lovely equations that describe how to rotate a point in arbitrary space around the origin. Or you can have one equation. Just looking around to see if anybody's frightened by me doing that. Is anybody slightly frightened by that? Everybody remembers how to do matrix multiplication, right? Matrix multiplication is both like strangely confusing and incredibly useful. Sorry, I should have said about halfway through there's going to be some pictures of dogs, because there was going to be a lot of maths, and then you go and here's some pictures of dogs. Matrices are great. Matrices are sheepdogs. They're just there to herd small equations into a tidy form that you can more easily use. And let me just explain matrix multiplication. The interesting thing about, well, I don't know if this makes it simpler or not, but I've taken all the maths out and just given you coloured blobs. So we're just going to multiply these two matrices of coloured blobs. And you can only multiply two matrices. This is the very important thing to remember. You can only multiply two matrices if the one on the left has got the same number of columns as the one on the right has rows. Shall I say that 3 or 4 times? Because, and I'll show you exactly how it works. All the explanations I've ever seen on paper of how you do matrix multiplication are incredibly confusing, whereas in fact, it's just kind of like a picture that you have to get in your head. And the picture is this. What you're going to do is you're going to take the first row on the left and the first column on the right, and then you're going to put them in, you're going to put the result of doing that into the first row and first column of the result. And the way you get the result is you take the row, and from your point of view, you rotate it clockwise, and then you've got, in this case, 3 rows of expressions. You multiply them together. I should have done a diagram for this, right? So you've taken the red line, you've turned it round, you've multiplied it by the blue column, and then you've got 3 terms, one after another, which is the red square, pale blue square, the red triangle, medium blue square, and the red circle, deep blue square. And you just add them together. And that's all you're doing all the way through. And that thing, if you want to sound like a mathematician, that thing is called a vector cross product, which it's an incantation, right? So you just say, take the vector cross product. But it's basically you just take that row and that column, multiply them together, put them in the same slot. And you just work your way through the entire matrix doing that. So row 1, column 1, row 1, column 2, you do exactly the same thing. Take the row, turn it through 90 degrees, multiply it out, add the terms together, put the result in the first row, second column. First row, third column, do exactly the same thing. First row, fourth column, do exactly the same thing. And then you just work your way through the entire thing. So you end up with a matrix that's got the same number of rows as the first one and the same number of columns as the second one. And why this is good is because if you've got two equations, like the two equations we've got for rotating an arbitrary point, you can just rearrange them into one matrix equation, which looks like that. So you can now all do matrix multiplication in your head, right? Because you've got that picture in your head. So what you do is you take so if you want to find out, sorry, where are we? Yeah, so the result for x is you take the point that you started with, which is xy, turn it on its side, and you get x cosine theta minus y sine theta, which is the equation at the top. And then you do the second column, and you get the second equation. And it's simple. You're just herding them together is all you're doing. The great thing about having matrices is, oh, we'll do the live coding now. It's be fun. The great thing about doing matrices is that you can do magical things when you put them together. I thought I'd do some live coding because why not? It seems to be in fashion this year, and I was sort of like hunting around for the right language to actually do a little bit of 3D live coding in. And I was thinking, oh, maybe I should do this in C++, or I should do it in JavaScript, in WebGL. And none of them had exactly that right mix of sort of like simplicity and explanation. And I found out that of all things, the Ruby matrix class is absolutely beautiful and does exactly what you want. So we're going to do some live coding in Ruby, but not very much. This is annoying. I actually have to. It is, yeah. Since two, it's there, and it kind of looks like this. It's a bit. Can I make that a bit bigger? Command function. Do that thing. Do that thing. You can see I did this just now. So IRB. So there is a matrix class, and the matrix class has. This is slightly annoying because it's a bit Ruby-ish. It's a bit like sort of like inventing your own idiom as you go along. But there is a factory method in matrix which looks like this. And although that looks like an array accessor, you're calling it on the class, and it turns into a factory method, and it creates an instance of matrix with those values. And you have to have the two sets of square brackets, because you're saying this is my matrix and this is the row inside it. And if you want more than one row, then you do that. 6. It looks like that, which is quite nice, and it's quite a nice way to play around with it. So, so we were playing around with 30 degrees, weren't we? So if we do sine theta is math.pi divided by 6, isn't it? 30 degrees, math.pi over 6. It's that. Yeah, if only I could program computers, life would be so much easier. There we go. So that is sine theta and cosine. Actually, what am I talking about? It is math dot sine of that. There we go. As I said earlier, it's exactly 0.5. Good. And okay, don't you just love floating point arithmetic? And then we want the other one, math dot cos is the same thing, math pi divided by 6, like that. And then we can just create our rotation matrix for rotating anything around 30 degrees. And that would look something like this. Our rotation matrix is a new instance of matrix, and it goes if I remember correctly, cosine theta minus sine theta sine theta cosine theta. Is anybody checking my workings as I go along? I think that's correct. It looks like that. Let's have a quick peek at. That's right, isn't it? No, it's the other way around. Cosine sine and then minus sine cosine. Brilliant. Great. Like that. And then if I have a point, so if my point is at 7, 8 was our example, equals matrix 7, 8. It's one of those. And then the magic is that if you want to find the rotated point, say P dot, that is just equal to, the order matters in matrix multiplication because it does, P times R, ta-da! Which is, I think, correct. Let's go back and have a look at the last version of the diagram, shall we? It was, oh no, it was the one right back at the very beginning, wasn't it? No, actually, I haven't got a diagram to check this against. Should we just imagine it's the right result?
Yeah, right.
It's right.
Yeah.
Yeah. Do we all feel it's right? Have we got a gut feeling? People are saying it's right. Yeah, that's good. Okay, crack on then.
If it's wrong, it's not wrong. It's an alternative right.
It's just an alternative. It's an alternative. It's an alternative maths. Yeah. I hope I'm not keeping track of time. I hope I'm doing kind of okay. I think I'm about halfway through, something like, yeah. The other important thing, if you're trying to do like a really basic understanding, the other little bit you've got to get in your head is translation, or just moving a point from A to B. So suppose you want to move a point by A and B, sorry, slightly confusing narration there, then the result is that the new x and new y are x plus A and y plus B. You've just added the translation to your original point to get your new point. But it turns out that there's a slightly more interesting way of doing translation. We have to go round the houses a little bit to get there. There is such a thing as the identity matrix, which is kind of like 1 in matrix land. So if you want to multiply a matrix by something and come out with the same thing that you started with, you multiply it by the identity matrix. And the identity matrix is just a diagonal of 1s through the middle. So if you just quickly do the matrix multiplication in your head again, which I'm sure you're actually doing that. It's a lot of fun. So the first element, the top left element of the result, is A times 1 plus B times 0 plus C times 0, so it's A. And the element to its right is A times 0 plus B times 1 plus C times 0, so it's B, and it just carries on all the way through. So the identity matrix, that thing with the diagonal of 1s going from left to right, you multiply it through and you just get the same thing that you started with, provided that the matrices can be multiplied because they've got the right number of rows and columns, obviously. And so, next mystery, W. W is great. In certain circumstances, and this will become really clear really soon, in certain circumstances, we're still, that looks like we might be suddenly doing 3D all of a sudden, but we're not. We're still doing 2D. We've got an X and a Y, and we've stuck a 1 on the end. And then in our new multiplication matrix, we've stuck a 1 at the bottom corner. And what that means is that when we do the multiplication, we get the rotated X and Y followed by a 1. It's one of these things, you're going to have to trust me, but only for a minute or two. It will begin to make sense. That thing on the end is called W. It's not part of the space that you're playing around with. It's not part of the game space or whatever. It's not part of the graphics. It's just called W, and it's a maths hack. And it's Yeah, they'd like you to think that they're all sort of like intellectual and highfalutin, but they hack. They hack. And the reason why that is so good is that you can now get, so originally we did translation by adding a bit into the point that we had, but we can do translation by multiplying. If we stick the A and the B that we want to translate down in that funny little position at the bottom left-hand corner of the matrix and put the identity W on the end, then you can see if you multiply that through, then you get the new X is X times 1, Y times 0, and 1 from the W of the point times A, and similarly B. So it turns out that you can get the translation by multiplying rather than adding, which may seem like a lot of faff, and why would you bother? And the reason why you bother is because of the real magic of these things, which we're building up to. We're building up to a moment of magic, if you like, mathsy kind of magic. It's quite geeky magic. So the really interesting thing you want to do is not rotate points that are on the y-axis or the x-axis, or points around the origin. You want to be able to rotate a point around anywhere in the space by anything you like. So the question is, how do you do that? So we've got this point on the left-hand side of the screen, and we want to rotate it by, I suppose that's about 75 degrees. Theta is 75 to a new point down there. But we start, the origin or the center that we're rotating around is not the origin of the coordinate system. It's somewhere else. What do you do? And the answer is this thing on the right. When you give matrices symbolic names, you usually give them capital letters. So what we're really trying to do, right, is we translate the whole thing by minus where the center of the rotation is going to be. Then we do the rotation, and then we translate the whole thing back to where the center of the rotation is. So in order to do that, just a little bit of notation really. T minus 1 means the inverse of t. So if the translation is I think in this case 3, 2 to get us to the point of the center, then t minus 1 is the inverse of that, minus 3, minus 2. The rotation is the rotation matrix that we've already seen, and then multiply it back out. And that means that if you spell that out in slightly bigger, longer format, it looks like that. So you're doing the translation matrix to get your center of rotation to the origin. You're doing your rotation, and then you're moving it back again. Now you could, if you really wanted to, multiply this out longhand, and you get quite a long, incomprehensible expression in the bottom left-hand corner of it. But why bother? Life's too short. Instead, let's just look at this. So I've just put the real values on there, just so that you can see what you do. And here, is that readable, or can I zoom it in a bit? Yeah, it's okay on the screen. Yeah. So exactly the same Ruby code that we were looking at before. Bring in the matrix, get the value for theta, get the value for cosine theta and sine theta, and just declare where your center is, and then create the inverse translation, which has got so minus center x minus center y, the same thing we're calling AB in the previous thing. So we've got one matrix which is called the translate inverse. We've got one matrix which is just the rotation matrix that we've already seen, and we've got one matrix which is the translate it back to where we were, exactly the same thing that we were just looking at. And it turns out you can just multiply all three of those together, which is why it's so nice to have the translation in the multiply form, even though it looks like kind of weird, because you can just arbitrarily concatenate these matrices together, and provided they're sort of like normal, what they call affine transformations, then you can do that, and you can do arbitrary things with them and just string them together. So we now have a transform matrix which does the whole thing in one step. And then we just say, well, our original was at that point, and the transformed is the original times the transform, and the result comes out. Normally, of course, you wouldn't. In real code, typically you wouldn't be doing this in Ruby. You'd be well, or you would, but you wouldn't actually be transforming the points in using the CPU. You'd probably create the transform that you want for the job, and then you'd hand that over to the GPU using OpenGL or something, and then you'd feed like a ton of data through the GPU, and just say multiply all this data by this transform. So instead of moving one point around rotation, you'd move the whole scary robot monster around by the rotation, because that's the model that you're rotating around. Oh, that's the end of the 2D bit, right? So we're going to do 3D bit now, because we've got all the tools. We've got all the mental tools we need to do 3D. Just a couple of points you need to bear in mind when you start thinking about 3D. The first is, when you think about 2D, what you're seeing on the screen is pretty much what's on the paper. So you're seeing the 2D space directly. Whereas when you're dealing with 3D, you've got a model of the world, you've got your game space, whatever, that you're moving things around in. And then you've somehow got to make it appear on that 2D space on the screen. And the way you typically handle this problem is you say, well, for every component I'm dealing with, there's a model view transform, which is transforming the model within the model space. And then there's a thing that takes the model space and turns it into the coordinates that the graphics output will understand. So, for instance, OpenGL just has this box, which I think goes from -1 to 1. 1 to -1, and then it goes into Z by 1, but it hasn't got its own perspective, so you actually have to apply the perspective yourself. So basically you take the view that your virtual camera has got and you translate it into the space that's in the output screen. But we're not going to do it. We're only going to talk about the model world bit, because it's slightly simpler. And once you've got your head around this, then you can pick up the rest. The other thing that you need to remember about 3D space is really confusing, is that it is handed. You've got handedness, and this is, if you think you've got X, Y, Z coordinates. So if you count them off on your hand, you've got X on the thumb, Y, and Z. So if you've got X going from your left to right across the screen and Y going up the screen, that means that Z is going backwards out of the screen. Whereas if you've got a right-handed coordinate system, you've got X going left to right across the screen, Y going up the screen, and then Z is coming out of the screen. And that can be incredibly confusing. Most things these days have right-handed coordinate systems, but sometimes you'll be working with a model in a 3D program and you have to kind of swap around between the two. And it's worth bearing in mind that that problem exists, and it's a source of confusion. I just kind of liked the pictures, so I thought I'd use them. So if you're trying to rotate something, we know how to rotate something on the XY plane. So here we've got a black blob, and we're thinking about rotating it through an angle a bit less than 180 around XY. What does that look like when you put it in 3D space? Well, it kind of looks like that. You just take the whole thing and think, well, that plane is somewhere in 3D space, and you can solve that like this. So you say, we've got a point which is X, Y, Z, and it's got a funky one on the end, W. And then in order to rotate it in the space, we've got the same rotation matrix that you saw before, but Z doesn't change because we're just rotating in the XY plane. Z doesn't change, so we just put a 1 in the identity bit for Z and a 1 for W. And that gives you a rotation in the XY plane in 3D space. Equally, I think you can see the bit where I ran out of time to prepare like really groovy looking graphics, and I just went, oh, I need to get to the end here, I'm tired. But I will do them eventually. Similarly, you can construct a matrix to get you to rotate you in the YZ plane, which may very well be that Z is coming out of the screen, Y is going up the screen. So it would be the one that's kind of parallel, be that kind of plane. But it really depends on which way the camera's looking. Anyway, it looks like that, and because you've just moved it down there. And similarly, oh, you've got one in the XZ plane as well, which I don't seem to have put in here. Terribly sorry about that. It'll be in the slides when I put them in. So the grand conclusion of all this is that we want to translate something around an arbitrary axis, in this case, in 3D space. So we've got this black blob, or black point, that we want to rotate around the purple matrix, which is pointing off in some odd direction away from the axes or the coordinates of the space. And the way you do that is, if you think about where that purple line is, rotate it first. This is kind of like doing the translation to get back to the origin. It's you want to simplify the problem. So first of all, you find out how far the purple line is away from the that would be the ZY. It would be the vertical plane this way. You find out how much you need to rotate it by to get it up into that space. And then you find out how much you need to rotate it back towards the Z, the blue one. And you rotate it through that. And then you've got your arbitrary axis. Excuse me. You've got your arbitrary axis in line with the Z axis of the coordinate space. So you've done one rotation to get it into the plane XY, and one rotation to get it right up into Z. Kind of looks like this. You can find those two angles. It depends on the data that you started with. But you've got the point at the end of the purple rotation. And you can just do some simple trigonometry again. And in this case, you want the ATAN, the arctangent of the X and Z of the original. Gosh, I wish I had some clear diagrams to explain this now, because you just want to find, you want to generate that angle from simple simple trigonometry, and then you rotate the whole thing round that angle that you find. This gives you your RY, because you're rotating around Y to get up into the XZ. And similarly, you do the same thing to rotate up into Z, and that you call that the RX. And then finally, the angle that you want to rotate around, you can now just rotate around Z, because it's now in the XY. It's in an XY plane. And then you put them all together, and you can do the same thing again. You can just multiply out the matrices. And I've kind of done the so you find the rotation into X, the rotation into Y. The rotation into Z is the actual angle that you were trying to rotate around the arbitrary axis, and then you just put it back where you found it in the first place. And that gives you a matrix that will do, and you can generate that matrix and apply it to your whole model again, and just move your model around in the whole model space. And of course, you can do the same thing that we did with the 2D matrix to translate it from a position that's not adjacent to the origin. So you can do like a translation at the beginning and a translation -1 at the end. And you can rotate anything around an arbitrary axis by these means. I think that's it. So my plan is, or my feeling is, that if you understand those simple building blocks of how rotation matrices work, it's actually more or less the hardest bit of 3D math. There's some other bits that you need to do. You need to understand normals and in order to do some of the rendering stuff. But mostly, once you've got those bits inside your head, and once you're comfortable handling them, there is no mystery, right? The rest is just bits and pieces that you put together. And here is a comforting dog, because I know there was quite a lot of maths, and I love those things, blue merles. Yeah, that's it. That really is it. How many people now feel that they can do 3D maths in their head?
Well, I don't feel I can do 3D maths, but I am fascinated to learn more. And wish I had that.
Yeah.
Could you share some links?
Yes, I've got some. I've got a lovely book which I've had for ages, which is a guy called Linda Amaral, which is graphics programming in Java. Wonderfully, I've had it for ages. But Linda Amaral wrote I think he wrote the same book in sort of like several languages over the years as fashions in languages change. There's also this thing which I am putting together at. Oh Lord, may require my glasses. That's the wrong one, isn't it? So some of those diagrams were made with some JavaScript, which I put on mrtony.green. So you can actually, what I'm hoping to do is build this into an article with interactive toys to play around with. So that allows you to sort of like just play and understand what's going on with the numbers. And I'll build some more of those, I hope, time permitting. And yeah, and one or two other resources I will find for you. Thanks very much.
Thank you.